Hello and welcome to this lecture series on chemical process modeling and simulation. We are in a series of lectures on modeling energy of systems where we are revisiting or visiting the fundamentals of thermodynamics, right? So after one lecture, a first lecture on an introduction to the basic principles of thermodynamics, we had a lecture that derived the criteria for thermodynamic equilibrium between two systems, and then we spent one entire lecture on entropy, and then we are in the fourth lecture, but that fourth lecture itself is in three parts. And the first part, which we covered just earlier, is on temperature. The second, this one, is on pressure, and the third, the subsequent one, will be on chemical potential. Taken together, these three lectures are on the intensive properties: temperature, pressure, and chemical potential. So this lecture talks about pressure. Pressure is seen as the driving force for expansion of a system so as to maximize entropy. Temperature was seen as the driving force for energy exchange, and that was specifically thermal energy exchange so as to maximize entropy. Pressure is seen as a driving force for expansion so as to maximize entropy. So we start with the entropy formulation, where the macroscopic state of a thermodynamic system is defined by its entropy, which means S is a function of various independent variables. We choose three variables. For one, the internal energy corresponding to heat interactions, and the second, which is relevant to this lecture, which is to do with moving boundaries and therefore volume changes, and that's an independent variable. The third is the amount of substance or number of moles of substance present in the system. This has to do with a boundary which could be permeable or impermeable. Now, therefore, if we state S is a function of UVN, then the total differential change in S could be due to either a differential change in U or V or N or some linear combination of all of these, and these slopes are defined as temperature, pressure over temperature, and negative of chemical potential over temperature. And this is we assign these definitions for these partial derivatives, and these are the intensive properties: temperature, pressure, and chemical potential, right? So if you notice, S is an extensive quantity, U is an extensive quantity, and therefore T becomes an intensive quantity, and so on and so forth, right? So thus we can write ds as du over T plus P dV over T minus mu dN over T. This is the entropy formulation. So now, what is pressure? Pressure measures the driving force for expanding the system boundaries, increasing the volume of a system or decreasing it so as to maximize the entropy. We are going to present this argument along similar lines of what we presented for temperature, right? So work is typically described as energy in transit due to force acting on a distance and is said to be stored as potential energy. So for conservative system, this is the change in the potential, stored potential energy, because of the force acting on a distance, and the total work done is simply the integral of f dx, and f is simply the gradient of the potential. The larger the force, greater the amount of work done. So viewed in a similar manner, entropy, okay, is the potential to displace a system's moving boundary and P over T is the driving force for it. Okay, so then the driving force is simply given by the gradient of the dou S, dou V at constant un. This is not Vn, this is un. So higher the pressure of the system, greater the tendency of the system to expand. And entropy measures the tendency of the volume of the system to increase. Now, in order to explain why pressure is a force for expansion, I can construct a similar argument as what was constructed in describing temperature, right, where there is a monetary transaction and so on and so forth. I will leave it to you to construct a similar argument along those lines. Instead, I am going to turn to another tool where we simplify, consider a very simple model, in fact oversimplified model, but it captures the essential physics of what is happening and reveals to us what is the underlying physics, and reveals to us a clear understanding of what pressure is. And for this we are going to consider a gas with n spherical particles. Each molecule is like a spherical particle that can either occupy a large or a small volume. And in fact we are not even going to look at a continuous space of volume. We are going to consider a lattice model. A lattice model is like, okay, there are slots, so you can put it's these spherical particles could be like beads, and then you can put one bead in one slot. So in the Indian beautiful rangolis that we make, in many of those rangolis you make these dots, and then you do draw around those dots or on those dots, right? So those dots can represent lattice points, for example, right? So this is another type of simplified model that we are employing, right? Just as we employed the analogies in understanding entropy, where we considered coin toss or die rolls or things like that. We have considered an analogy in understanding temperature by constructing an analogy with financial transaction. Here, another simple model that is constructed is a lattice model. So, through this lattice model, what we are going to do is answer this question. We have learned in schools that gases always prefer to expand to the largest possible volume, in the absence of course, some external forces that are holding them, forcing them to be confined to a fixed small volume. Why is this tendency, the preference to expand to the largest possible volume? Of course, this maximizes entropy, and that is what we will see. Gases tend to expand to maximize entropy, and pressure is the driving force for the same. This is the conclusion that we are going to come to. For this, all right, let us consider a simple lattice model of a gas, which is easy to visualize and illustrate. This is also from Bell and Bromberg's Molecular Driving Forces. So I urge you to consult this book if you want to get a little bit more details. So here is a lattice model. So there are three particular scenarios. So you can think of these as slots. So there are how many spherical particles in all these three scenarios? There are three spherical particles. But there are three slots in which three spherical particles are put. Here in case B, there are four slots in which three spherical particles are put. And in case A, there are five slots in which three spherical particles are placed, right? So if we look at the number of these slots as a measure of volume, it's a one-dimensional system, right? So you measure volume in units of a single length, and since it is a lattice, you just have discrete values only possible, 1 2 3 4 5, right? So here the volume is 5 in case A, in case B the volume is 4, in case C the volume is 3. So there are three possible cases, right? So the three balls are therefore the three molecules, right, spread out and occupy the entire volume of 5 positions, which is this preferred to expand to the largest possible volume case, or stay contained in a smaller volume of 4 positions, the last one not even being available, or stay bunched up in 3 consecutive positions, the last two not even being available. Now, this, I cannot say that these three are equivalent to having 5 lattice positions, and then the three are distributed in one way. 5 lattice positions, the fifth one is an empty vacant site. 5 lattice positions, the last two are vacant sites. No, that's not what we are talking about. We are talking literally about the boundary moving, so therefore I am adding lattice sites, right? So in this case, I have minimum number of lattice sites, just 3 lattice sites here. Now I have added one more lattice site. In other words, the boundary has expanded. The moving boundary has moved to include one more site. And here, in this case, the boundary has moved to include 2 more sites, of course. The position of these balls and where they are placed is somewhat arbitrary. That is not the idea. It's that the number of sites available is increased, which corresponds to the volume being increased. So in 1D, as I mentioned, volume is simply the number of lattice sites. So consider this simple 1D lattice model of a gas, right? So if I call my volume as M and the number of particles is 3 in all the cases, so these three are 3 possible macro states or compositions. What are the 3 macro states? Where the volume is 5, where the volume is 4, where the volume is 3. What are the micro states? Now I can put these 3 balls in 5 lattice sites in many ways. So each arrangement of the balls, say maybe 1, 2, 3, blank, 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 1, 2, 3. Like these would be different micro states or sequences of arrangement of the balls and blanks, right? But the composition is that there are total of 5 lattice sites, or 4 lattice sites, or 3 lattice sites for n being fixed. Okay, so this is typically a microstate or a sequence. This is also a microstate or a sequence, and this is the only microstate or a sequence possible when you can take 3 balls and put them in 3 lattice sites. There is only one way you can do the arrangement, and so the number of microstates is simply 1. And how do you calculate the multiplicity of each of these macro states or compositions? Simply you just say I am taking 3 particles in certain number of positions, then m factorial by n factorial times m minus n factorial. So what is the multiplicity of each macro state? In case 1, I can put 3 particles in 5 sites in 10 different ways. Case 2, I can put 3 particles in 4 sites in 4 different ways. In other words, the blank can either be in site 1 or 2 or 3 or 4. There are 4 different ways. And case 3, the multiplicity is simply 1. So the total number of microstates is equal to 15 in this case. Probability of each microstate is simply 1 over 15. All the microstates are equally likely. Now, what are the probability of the macro states? If you look at it, the probability of this macro state where you have maximum volume is 10 over 15 or 2/3. Whereas the probability of this macro state, second macro state with one less volume, is 4 over 15, and the probability of the macro state where you have all 3 balls in just 3 lattice sites and the volume is simply 3 is 1 over 15. There is only one microstate and there is only one macrostate corresponding to this, right? So once again, what do we find out? Maximizing the volume maximizes multiplicity of the macro state, and therefore that macro state that corresponds to maximum multiplicity, right, is the preferred macro state. That is the hypothesis, isn't it? So the rest state of the rest macroscopic state of a thermodynamic system corresponds to maximum entropy, and therefore this, we can see that pressure, or rather, let's come back to pressure. We have not talked about pressure here yet, all right? But the balls try to push against the boundaries of the lattice sites to include more and more volume. That is the idea, right? So the gases expand to occupy maximum volume possible. So now we come back to pressure again and consider this example of a system comprising two subsystems. The system itself has an isolating boundary, and therefore it does not have any kind of interaction with the surroundings, and this is an internal system boundary. At equilibrium, this boundary is going to be made moving. Initially it could be non-moving, right? So initially I could place this boundary at one corner or the other corner or wherever it is, just a little bit of volume here or a little bit of volume there or whatever, and then see what happens. Consider an isolated system with two subsystems separated by an internal moving boundary. So this is another example that I'm giving to illustrate pressure, right? So similar analogy can be constructed for temperature also. If you're interested, I urge you to try and do this. Such analogies have been presented, such examples have been presented in postulational and statistical thermodynamics by Y.V.C. Rao, as well as Herbert Callan's thermodynamics and thermostatistics. So if the degree of freedom of a subsystem is volume, that is the only degree of freedom that we are considering now, the number of molecules is fixed and the boundary is perfectly insulating so that there is no exchange of heat. So the degree of freedom of subsystem, sorry, I've put a system here again, of a subsystem is volume, which means the boundary is moving and therefore can increase or decrease the volume. The subsystem will spread out into the largest possible volume in order to maximize its multiplicity. The driving force for this expansion is pressure. So far so good. This expansion will last until the pressure of one subsystem equals that of the other, so that the net driving forces are always balanced and then there is no net displacement of the moving boundary. So far so good. But if the multiplicity increases by expansion and the internal boundary is moving, wouldn't the expansion of subsystem 1's volume decrease the volume of subsystem 2 and thereby decrease the multiplicity of the other? Which means, shouldn't subsystem 2 resist this expansion of the first subsystem in order to maximize its entropy, right? In other words, shouldn't subsystem 2 try to exert pressure on subsystem 1? Yes, of course this happens. This is what is the idea. Ultimately, when these two pressures are equal, that is when pressure exerted by subsystem 1 and pressure exerted by subsystem 2, when they become equal, that is when you reach the rest state or the equilibrium state. This is exactly what we were also talking about in the analogy money for gadget financial transaction. The benefit accrued by both parties have to become equal. So the entire system is isolated, therefore at equilibrium ds is equal to 0. Till equilibrium is achieved, the net entropy increases. So let us consider an example. Here is a fundamental equation for entropy. S is equal to sum k u power 1 by 3, v power 1 by 3, n power 1 by 3. Now, in constructing such hypothetical fundamental equations, you have to keep in mind that u, v and n are extensive properties, and S is also an extensive property, and therefore if U is doubled, V is doubled, N is doubled, S has to be doubled, and so on and so forth. K has to be a positive constant because entropy cannot be negative. For that matter, none of these can be negative. Energy cannot be negative, volume cannot be negative, number cannot be negative. So U, V and N are internal energy, volume and number of moles of a species. This is valid for both subsystems and hence the overall system. So you just put subscripts Ka, UVA, VA, NA, KB, UV, VB, NB and so on and so forth. In this case I have used 1 and 2, so K1, U1, V1, N1 and so on and so forth. So let's, for simplicity, assign the following initial values for the subsystems. K1 and K2 we just take to be 1. This is just some hypothetical system. U1 and U2 is 1 megajoule and V1 is N1 and N2 are 1 mole. Now in one case V1 is 0.05 meter cube, the other case V2 is 1.95 meter cube, so that the total volume is 2 meter cube, right? And that is fixed. The total internal energy is 2 megajoules, that is fixed, and the total number of moles is 2 moles, that is fixed, because the total system, overall system, the entire system is isolated, right? So therefore that none of these total numbers U1 plus U2 cannot change, V1 plus V2 cannot change, N1 plus N2 cannot change. Now this is U1 and U2 are not going to change, N1 and N2 are not going to change. We are only considering this degree of freedom. So V1 and V2 will change subject to the constraint that V1 plus V2 will be equal to 2 meter cube, right? So that is what we are going to do. And so if you recall the previous slides picture, so you have a isolated system, and this initial state corresponds to the moving boundary placed close to one end of the system, where the initial volume here is just 0.95 meter cube, and then the rest of the volume is 1.95 meter cube, right? And this sort of corresponds to, therefore, the initial state where subsystem 1 will have a higher pressure than subsystem 2 from common sense. So now initially, what is the total entropy of the two subsystems? You can calculate this, substitute all of these into this. So S1 plus S2, that is 1.62 joule per Kelvin. Now suppose the internal boundary is made moving, subsystem 1 is going to expand. Why is subsystem 1 going to expand? Because the volume of subsystem 1 is very, very small, right? And therefore you are containing the same amount of energy and the same number of moles in such a small tiny volume compared to a larger volume, and therefore there is going to be a higher pressure here than here. Subsystem 1 has a higher internal pressure to start with than subsystem 2, and the net pressure is going to be acting from subsystem 1 to subsystem 2, causing subsystem 1 to expand. So there is the maximum entropy to be found. So let us try for different values of V1 and V2, that is the degree of freedom. So we can change V1 and V2. V2 is simply 2 minus V1 because the V1 plus V2 equal to 2 meter cube is a constraint. So there is only one independent variable really. So let us change the volume and then see where are we going to find the maximum entropy. So if one were to plot entropy as a function of volume, the maximum entropy is found to be 2 joule per Kelvin, and that corresponds to the volume being 1 meter cube. In other words, both have the same volumes. Well, you should not mistake that the criterion for the mechanical equilibrium is that the volumes have become equal. That was simply the case because U1, U2 was equal to 1 megajoule, N1, N2 was equal to 1 moles. So I assigned this as a homework for you to try. Take U1 to be greater than U2 or U2 to be greater than U1. Alright. Similarly, take N1 to be greater than N2 or N2 to be greater than N1. Assign some value. Alright. And then rework this whole thing. You have S is equal to K U V N all power 1 by 3. Let K1, K2 be equal to 1. Alright. Or you can even change the constants for that matter. Then you will see that this maximum will shift away from this 1 meter cube volume. Alright. That is for you to try and find out. The maximum volume corresponds to V1 is equal to 1 meter cube equal to V2. what happens to the pressure of the two subsystems. So what is the pressure of the two subsystems? The pressure is calculated by this definition of minus P by T being dou S dou V with respect to constant U and N. For subsystem 1, when you take S is equal to cube root of K U V N, so you get this expression doing the derivative with respect to volume, keeping U and N constant. Similar expression is for the pressure of the subsystem 2 at maximum of entropy of 2 joule per Kelvin, and the volume, both volumes of course being 1 meter cube. The pressures of the two subsystems are equal, and this equal pressure happens to be 0.1111 bar. So if you were to plot the pressures of the subsystems, it is at this point where the slopes, basically the slopes, become equal, and that is the point corresponding to mechanical equilibrium between the two subsystems. So pressure, to summarize, is the driving force for expansion, increase of system volume so as to maximize its entropy. With this, we come to the end of this lecture. I hope this lecture was understandable for all of you. If you have any comments, any questions, as always, please feel free to contact me. You can leave the questions on the comments section of the YouTube channel, or you can reach me in person through other means. Thank you for listening to this lecture. Have a nice day.